Now, what's neat is coming around the time of Romer in Denmark, they were able to, Galileo created the telescope, and that really opened up astronomy to be able to see things much more clearly. And one of the things they were able to do was observe Jupiter. And at this point, they knew now that the sun was in the middle of the solar system, the Earth was going around in a orbit, and Jupiter was in an orbit as well. And then around Jupiter, we have moons. And so what's really interesting here is that they noticed that the time period for the orbit of one of Jupiter's moons varied slightly. And what happened is as, you can see Earth here, it takes one Earth year to go around, right? But Jupiter takes 11.9 years, so it's going kind of slow here, right? So there's a point at which Earth is approaching Jupiter, and there's a point at which Earth is leaving Jupiter. And when Earth was moving away from Jupiter, they noticed that it took a longer time period for this moon to make a full orbit. And then the Earth moving towards Jupiter, and it took a shorter amount of time. And they knew that, the orbits are very consistent, right? Our orbit around the sun, the orbit of the moon and the Earth is very consistent. So they figured that it had to do with the speed of light, the fact that we're approaching Jupiter or that we're leaving Jupiter, going away from it, affects the time period that we measure that light. And there is a finite measurement of light, even though it's very, very fast. Now in America, coming into the close of the 19th into the 20th century, um, they made this experiment in 1920 that was pretty ingenious. And what they did was they set up a light source on a mountain, on Mount Wilson, and then they put a stationary mirror on Mount Baldy. And what they did was they rotated this mirror, and they shined the light at it. So the light would leave this, hit the mirror, bounce off the stationary mirror, hit the mirror on the other side, and then come into the observer's view. So what happened was if you spin it too quickly, it'll miss, and then if you spin it too slowly, it'll miss because the light's got to be able to hit. This has got to be able to rotate while that light is traveling, and then hit back and then go there. And so through the distance, they knew, how far away the mountains were. They knew the geometrical, dimensions of the rotating apparatus. They used trigonometry and the angular speed to be able to figure out the speed of light, and they actually got very, very close. Um, the speed of light is very close to 3 times 10 to the 8th meters per second. 3/1000ths, right, of so very, very close to 3 times 10 to the 8th. And yeah, and this showed that the speed of light, is not infinite, but it's very, very, very fast. And what's so profound about Maxwell's equation and what he did in 1831, well, he was born in 1831, died in 1879, is the speed of an electromagnetic wave. And what's crazy is up until Maxwell's discovery of the existence and speed of electromagnetic waves, we didn't know that electromagnetic waves. We didn't know light was an actual electromagnetic wave, and this was a huge connection. Maxwell had a huge influence in our understanding of electricity and magnetism, and he was really really influenced and encouraged by Faraday's work. And so Maxwell was a brilliant mathematician. He was able to take a lot of what Faraday did and mathematically understand what was happening, and including the fact that if you have an electric field, magnetic field intertwined, you've got an electromagnetic wave and you have a specific speed to it. And he predicted these waves with his calculations. This is a little bit earlier on in before that 1920 experiment. He compared the electric fields and magnetic fields and calculated the speed of these waves. And you should recognize these two. These are our constants that we've been using based on a vacuum that we've been using. And so 1 over the square root of these values gives us the speed of light and electromagnetic waves, which include radio and X-ray and all the other kinds, invisible light. And we'll be unpacking these different ones. One of the critical things that you guys read in David Bodanis's book, equals mc squared, was the fact that the speed of light, c, the speed of light is the speed limit of the universe. And according to Einstein's theory of relativity, nothing can go faster than the speed of light. And this is the limit. And so we don't have time to dive into relativity very deeply. There's a lot of interesting things that you can research on your own online, but it's important to know that nothing goes faster than the speed of light in a vacuum. All right, so now we're ready to take a look at the electromagnetic spectrum, which includes all the different kinds of electromagnetic rays. Remember, electromagnetic rays, or just light in general, any electromagnetic wave is made of an intertwined electric field and magnetic field. And what we're going to do in this list is look at the different kinds, how they were discovered, and it's kind of a neat story. The longest wavelength is the radio wave. That's what we're going to start with. So here's the longest wavelength down here. Longest wavelength. And then over here, this is the smallest wavelength. So gamma rays have the smallest wavelength. However, in terms of energy and frequency, so frequency has the lowest frequency radio waves, therefore the lowest energy. And then the highest frequency and highest energy is gamma, has the highest frequency, highest energy. So radio waves have the longest wavelength. Maxwell predicted these, in 1864, and then in 1885 and 1889, Heinrich Hertz created them in the lab and created the first radio waves. And they're used to transmit radio and television signals. These were critical in our aircraft as we communicated with other pilots and with air traffic controllers using radio waves coming from our airplane and then back and forth from air traffic control. Satellite communication can use radio waves, and there's some very, very large receivers that are being used for astronomy to be able to map astronomical objects that are producing radio waves. And here is a large receiver. The question I wanted to ask you guys is, why does this have to be so big? Well, radio waves are the absolute longest, and so radio waves, span the greatest amount of distance. And so if you imagine, an astronomical object, producing a radio wave, and when it hits us, maybe it's something like this, right? And then it hits the antenna, and can be received. If the antenna is real tiny, it's not going to be able to interpret that. Microwaves are the next, and microwaves have smaller wavelengths than radio, therefore just slightly higher frequency and slightly higher energy. And they're used for multiple different things. When we think of a microwave, we think of a microwave oven. What ends up happening with a microwave oven is that water at certain microwave frequencies and fat molecules resonate and shake, and as they resonate, they heat up the surrounding food and it heats up, right? For radar, they're using a different, in microwave, in GPS and cell phone communication, are using a different set of microwaves, different wavelengths, and they can be used for, the communication. And this can actually be used for astronomy as well. You can have, specific antennas looking at microwaves coming from distant objects in space. One of the interesting things is the cosmic microwave background radiation. um, with the creation of the universe, the beginning of the universe, the the theory is that there was nothing, and then you have matter appearing and then exploding very rapidly, and this rapid expansion created electromagnetic waves, and so when we look out into space, and they actually discovered this, way back in 1964, accidentally actually, they discovered this background radiation in the universe, and this surrounds the whole universe. And we see this microwave radiation, and being able to say or be able to see some evidence for the creation of the universe, that there was actually a beginning. Okay, so let's think about this. Let's say we have a prism, we have white light coming in here. It goes through the prism, spreads out, and comes to the other side. What if you place a thermometer just on the other side of the red light there? Well, it turns out that scientists did that, and there was actually an increase in temperature inside the thermometer, and the temperature increased. And so they figured, okay, well, maybe there's something there, and it turns out that there is something there. This is in 1800. Herschel discovered infrared by placing a thermometer there, and in objects that have a temperature below 500 degrees only produce infrared. So our bodies produce infrared. The things surrounding us on Earth, produce infrared. If we shut all the lights off, right, and nothing's reflecting, it's just gonna, we're not going to see anything with our eyes because we cannot perceive infrared light. But it's shooting out electromagnetic waves, and we're shooting those out from our bodies. So the question is, why is this glowing then? If we shut all the lights off, we'd actually see this glowing. And what's actually happening here is there is visible light being created, and that's because it's so hot. One of the simulations that we've used in the thermal unit that'll be important for you if you missed the lesson is to go back and look up black body spectrum under PhET in a Google search, and move that temperature up and down, and you'll see that as you get to certain temperatures, you actually have visible light being created.